Today, you're going to learn something that you actually really already know how to do. It's just kind of an extension of our thought process with regarding derivatives, and it's called linear approximation. Tomorrow we'll do differentials. Um, Tomorrow's a little bit more confusing, but it's not too bad. But linearization, super helpful. Okay, do I use this? Yes, we definitely use this in calculus as you move forward. And the idea is this: if you have a curve given an x value and f of x, so that's our coordinate, x, f of x. Everybody okay with that? All right. Wow, it's snowing. Yeah, it's like a blizzard. Early out, early out, early out, early out. All right. So here's the idea of linearization. The key part of linearization is line. We're going to make something linear. And it's really to focus on a small specific region. Okay. If I focus on this window right here, notice that if I were to draw the line that was tangent to the curve at x, would you agree that that line looks like the function? That they are nearly one and the same in that window. And if you're not convinced, just say, well, you could zoom in even smaller like that. And the idea is that any curve, if you zoom in close enough, it should look like a line, right? I mean, it's that whole idea that a circle doesn't have any sides to it, does it? But if you would zoom in on any part of the circle, if you zoom in close enough, it would kind of just look like a line, wouldn't it? And so linearization is helpful. Why would the linearization of a function be useful? It helps us estimate values in close proximity. And it's no big deal. We want to write an equation for the linearization. We just write the equation for the line tangent. And so x, f of x, happens to be your point. Yep. And then anybody know what your slope would be? F prime of x. So we would have y minus f of x is equal to f prime of x times x minus, that x1. And that's really just our equation for linearization. Nothing new, right? So let's find the linearization of the following functions. And after that, let's apply it so we can understand what would it be used for, okay? Find the linearization of the following functions. Same thing we've always done. Identify the slope and a point on the line. Point on the line, yes. As opposed to? Oh, um, so we said that the slope is f prime, yeah. Okay, so the point on the line is going to be what? 1, 3. How'd you get the 3? Plugged it in. How do I determine the slope? Take the derivative. And the derivative of 4x squared minus 1 is? Isn't it neat when we can do it so quickly? And so, the slope is then 8 So y minus 3 equals 8 times x minus 1. Now you could write in slope-intercept form, y minus 3 is equal to 8x minus 8. So y is equal to 8x minus 5. And that's the linearization. So you already knew how to do that, right? Okay. So the application will be slightly different. Yes. The slope is not 8x. The derivative is 8x, and this tells us the slope at any spot. So it tells us slope at 1. At x equals 2, the slope would be 16. At x equals 8, the slope would be 64. At x equals 0, the slope would be 0. Better? Okay, y equals negative sine of 2x at x equals pi over 2. Point on the line? Uh, 2 times pi over 2 is pi, and the sine of pi is all right, so we don't remember. So we're looking at this spot right here. Can everybody picture that? What's the coordinate? Is sine the x value or the y value? Sine is the y value. Cosine is the x value. So, so the sine of negative pi is 0. How do I determine slope? Find y prime. So y prime is equal to chain rule. Very good. Derivative of the inside is, as D. Weiland said, 2. So I've got negative 2 times the cosine of 2x. Great. Now plug in. So I get the cosine of pi is negative 1 times negative 2 is 2. So y minus 0 is equal to 2 times x minus pi over 2. Or y is equal to 2x minus pi. That's the linearization. I know you guys can do this skill. The question is, do you understand that if they ask on the AP exam, find the linearization, that you'd just be finding the equation for the line tangent? What would help you remember that? Linearization, line, yeah. Probably find a derivative. Okay. So this is it. We're going to do this and you're done. You'll get a worksheet. And then it's Office Monday. Find the linearization of f of x equals 4 minus x and use it to approximate the value of the square root of 3.99 and the square root of 4.1. Provide a drawing to determine if the approximation is an underestimate or overestimate. Okay. Now, just so you guys can appreciate it for a second here, if I ask you what the square root of 3.99 is, all you do is you go to your calculator, you type in square root of 3.99, and press enter, and you get that. In fact, now you don't even need to have a calculator. You can just take out your phone, right? Or you take out your Chromebook, you go to Desmos, or you go to some other type of site, and you can punch it in. You have relatives that remember when calculators couldn't do that computation, where they could simply just add, subtract, multiply, or divide. You're like, big deal. Well, just remember that calculus was developed under a guy by the name of Isaac Newton in the 1600s, where he, forget about being able to punch something in. I mean, he was centuries away from being able to punch something in like that, right? So how would he come up with the square root of 3.99? Probably using the linearization of a function. That's a great idea. That's exactly what he would do. Okay. What's that? So you come up with these awkward values, And how do you approximate? We all know the square root of 3.99 is irrational, correct? But the fact is we always settle for approximations. We settle for, say, 1.997 or 1.995 or something like that. Would you agree that 1.9975 is a good approximation? You're going to see the type of approximation we come up with using linearization. So it says find this linearization, or find the linearization. I just need slope and I need a point. And this is the real key. This is the whole understanding piece that people screw up all the time. So this is the only part you really got to lean into. Anybody want to guess the x value that I used for this linearization? Okay, so we got 0.1, we got 0.99, we got 0, 0.01. People are just guessing right now. Anybody want to make a different guess? 1, 5. Okay, it's 0. Now, I'm going to show you why it's 0, okay? I'm going to show you why it's 0. We want to approximate these values, correct? What value would you plug in for x that would bring you close to these values? Right, you would come up with the square root of 4, right? So you got to decide the x value that would bring you close. Now, you guys might say to yourself, you say, well, Mr. Gentz, do I always choose 0? No, not always. If I change the linearization function, I said f of x instead of the square root of 4 minus x. Let's just say I said the square root of x. Then what would you choose? 4. You got to choose the x value that's going to get you close. Remember, linearization, it works. It works right here, but if I were to, draw then the line like that, well, you can see we start to fall apart out here, don't we? All of a sudden, we're not very close anymore at all. So we want to choose values that can bring us close. So 0 brings us close. Plug in 0, what do you get? 2. Great. How do I find the slope? Take the derivative. How do I do the derivative of that? Chain rule, super awesome. Square root of u, 4 minus x, derivative of 4 minus x, -1, derivative root of u. So I get -1 over 2 roots of 4 minus x. What do I do with that? Plug in what? 0. 4 minus 0, square root of 4 times 2, -1 over 4. It's really nice to pick a value that will produce a rational number. So to your point, could I have chosen x was equal to, say, 0.005? Well, plugging that in, it doesn't produce a value that I then know either, does it? So, yeah, 0's between them, so that's a nice idea, but suppose I had square root of 3.99 and square root of 3.9. Well, it wouldn't be between them, would it? But you still choose 0 in that situation. Okay. All right. Great. Let's write our equation. We've got y is equal to -1 over 4x plus 2. I mean, this is the y-intercept, isn't it? Okay. So we are going to estimate these values. I'm going to estimate those values. I want to estimate the square root of 3.99. What would you plug in for x to produce 3.99? 0.01 or 1/100th, correct? I'm going to plug in 1/100th. What do I plug it into? I plug it into negative 1/4 x plus 2. And that's going to produce a y value for me. So negative 1/4 times 1/100 plus 2. And you get negative 1/400 plus 2. I'm going to create a common denominator. Negative 1/400 plus 800/400. And that produces what? So apparently our claim is that 799/400 is approximately the square root of 3.99. Now, I'm going to go back and I'm going to check that out to see how close it is because, we're a little bit skeptical of these estimations. Would Newton be within good standing if you were to use this rational number as an approximation? Wow. I mean, that's close. Like if I were to square that, I'm supposed to come up with 3.99. You come up with 3.990006. Like that's tens, hundreds, thousands, 10,000s, 100,000, 6 millionths. I mean, you're within 6 millionths of squaring it properly, right? Not close enough for Katie, okay? And that will be fine, all right? Katie can choose another method. And Newton came up with another method to come even closer if you would like. So, so that's one way. We just estimated, square root of 3.99. Let's estimate the square root of 4.1. No, it says use it to approximate the value of square root of 3.99 and square root of 4.1. So let's estimate the square root of 4.1. So I need to choose an x value, and it's going to produce a y value. I plug in negative 1/4 x plus 2. What would you plug in for x to produce 4.1? Negative 1/10. So I'm looking at this square root of 4 minus x, and I need to come up with 4.1. How are you going to get 4.1? Well, you would have to add 0.1 to 4. So it's going to be 4 minus a negative 0.1, or negative 1/10. And I get, it looks like Dylan's already gone through it, I get 1/40 plus 2, which is 1/40 plus 80/40, or 81/40. Now again, I like to check and see how close I am. Square root of 4.1, it looks like we get 2.0248. If I do 81 and divide it by 40, I get 2.025. Looks like it's pretty close. If I square it, do I get that 4.1? You're really within the ballpark. Okay. All right. Now, the last question is this: Are these overestimations or underestimations? Is that an overestimation or under? Overestimation or under? It looked like we were over. It's pretty easy to confirm that you're an overestimation, though. I'm just going to show you real quick how to do it. Super easy. What does a graph of 4 minus square root of 4 minus x look like? Square root guy, right? Shifted to the right 4. And since the x is negative on the inside, it's a, everybody agree? Where are we finding the equation for the line tangent? At 0, 2, right? Which is that spot. If you draw the tangent line, is the tangent line above or below the curve? This tangent line is above. So therefore, everything that this line produces will be an overestimation. So if you simply look at the original curve and you look at the tangent line, that will tell you whether you're an overestimate or an underestimate. I will ask for your final answers in the test to be in rational form. This guy? What would you plug in to make 0? 4. So therefore it's shifted 4 units to the right. The negative is on the inside, so that affects it horizontally. So it's going to be a horizontal reflection. And if you were to consider this domain, 4 minus x is greater than or equal to 0, add or subtract 4 negative x greater than or equal to negative 4, so x is less than or equal to 4. Those are the values you can plug in, and you notice how the graph is everything that is to this side of 4. Okay. All right, good work. So again, if you were to plug in the value of 1/100th, that would be plugging in this value right here. This is an overestimation. If you were to plug in negative 1/10th, that would be this value right here. Still an overestimation. The graph is always, the line is always on top of the graph, always an overestimation. All right. Hey, guess what? I've got a worksheet for you guys.